In the third part of this video on inheritance and polymorphism, we will define polymorphism and explain the type compatibility rules associated with it, and then explain the mechanism of dynamic binding and illustrate it with an example. We begin by defining polymorphism. The word polymorphism literally means many forms. In the context of Java, we use this term to refer to the ability to have the type of a reference be a superclass that refers to an object of one of its subclasses. This capability requires that we then have rules that govern type compatibility that specify which kind of assignments are permitted. Objects of a subclass can be assigned to a reference of the superclass. This is usually referred to as an upcast because the object is being assigned to a class higher up the inheritance hierarchy. Assignments in the reverse direction are called downcasts. They require explicit typecasts because they are potentially unsafe. There is a possibility that downcasts will cause a class cast exception at runtime. If the object doesn't match the type it is being cast to. These rules are similar to the rules associated with primitive types that require an explicit cast for narrowing assignments but permit widening assignments. Now we are ready to explain dynamic binding, which is really the main reason for inheritance and polymorphism. To begin, it is important to understand that when an overridden method is invoked on a reference to the superclass, the actual method being called can only be determined at runtime. The determination of which method to call is referred to as dynamic binding. Recall that in programming language terminology, dynamic events are ones that occur at runtime. The way this determination is made is by examining the type of the object. It is the method in the class that defines the type of the object that is called. By comparison with overloading, the determination of which method to call is referred to as static binding, meaning that it can be done at compile time because the method's signatures are different. Now let's examine a different main class that uses the same student hierarchy that we discussed in Part 2. Notice the first difference from the previous version. We have declared an array of type student, and to it we have assigned three different kinds of students, one of type graduate, one of type undergraduate, and one of type student. This is an illustration of polymorphism. We have assigned two references to objects of subclasses to a reference whose type is a superclass. In both cases, it is an upcast, so it does not require a typecast. The next difference is the loop that follows. It is a for each style loop. It is always preferable to use such a loop whenever we can because it is simpler. Recall that in order to be able to use it, we must be traversing the whole array in forward order, have no need to use the array subscript, and be accessing, not modifying, the array elements. Inside the loop, we call the course completed method to indicate that the student completed a 3-credit-hour course with an A. Next, we display the student object with a call to the toString method. Although including the toString was unnecessary because it would have been called regardless, we added it for emphasis because it is the call to this method that involves the dynamic binding. The first time through the loop, the toString method of the graduate class will be called. The remaining 2 times, the one from student will be called. Next is another for each loop. Inside is a call to the method of the graduate class, meets master's requirement. Notice that this call requires an explicit downcast. Try removing that downcast and you will see that the program does not compile. The reason being that the reference type of the loop variable is student and this method is not defined in the student class. Before we run this one, you may want to pause to see whether you can predict what will occur when the program runs, especially during the second loop. Okay, let's run it. Notice that the graduate toString method is called the first time, and the one from the student class the second two times. But look what occurred with the second loop. The first time through, the downcast was fine because the first array of the object is of type graduate. But the second time through the loop, a class cast exception was thrown. The reason is that the second element of the array is not of type graduate. Having now completed our initial discussion of inheritance, polymorphism, and finally dynamic binding, for the sake of completeness, we conclude with a topic that we have intentionally avoided until now. It is the access modifier protected. Let's review what we have already observed about the accessibility of private names defined in the superclass from one of its subclasses. First, recall that private data in a superclass cannot be accessed from any method in the subclass. Second, private methods defined in a superclass cannot be called by methods in a subclass. The reason for this restriction is to preserve the benefits of information hiding. Subclasses are already coupled with their superclasses by the inheritance relationship, which means affording them some greater privileges is less problematic. The access modifier protected accomplishes that goal. Unfortunately, although declaring data or methods as protected makes them accessible to subclasses, it also makes them accessible to every other class in the same package. This is different from the meaning of protected in C++, which does not have packages. In the original version of Java, there was an accessibility mode private protected, which restricted access only to subclasses, but it was later removed. Consequently, the protected accessibility mode should be used with great discretion. The practice we recommend is that whenever it is used in an inheritance hierarchy, that hierarchy should be placed in its own package or subpackage so as not to overexpose the names declared protected.